master students from the Institute of Geographic Sciences and Natural Resource Research. It's my pleasure to present on the topic temperature and precipitation jointly regulated the shifts of vegetation phenology in Yang Mountain during 2000–2022. I will introduce this from the four aspects. Vegetation phenology encompasses the cyclical life events of plants, driven by their physiological attributes and the environment. The events typically following an annual cycle with seasonal patterns affecting the spatial temporal dynamics of vegetation's growth and development. The key phenological metrics include the start of the growing season (SOS), the peak of the growing season (POS), the end of the growing season (EOS), and the growing season length (GSL). Moreover, in context of rapid climate change, vegetation phenology is considered to be the most direct and sensitive indicator of seasonal and interannual changes in environment conditions. Meanwhile, changes in vegetation phenology indirectly regulate ecosystem carbon uptake and productivity by regulating transpiration, respiration, and photosynthesis of vegetation. At present, driven by the intensification of global warming and regional changes, the Northern Hemisphere is showing an overall trend of varying degrees of earlier the start of season, later the end of season, and longer the growing seasons. Regarding the spatial temporal dynamics of POS in Northern Hemisphere, recent lectures has two contrasting findings. Based on individual like Gossamer's work, POS showed an insignificantly advancement in Northern Hemisphere temperature those over the past 34 years. But based on GPP data, GIS research found no significant the peak of the growing season trend in my latitude regions. The trend changes in vegetation phenology was significantly influenced by chemical factors such as temperature, precipitation, atmospheric saturated water vapor pressure difference, soil moisture, and the photo period. Among them, the large number of studies have found that temperature and precipitation are main factors affecting the vegetation phenology. Besides, phenological parameters themselves have certain physiological correlations. Some studies have already found the vegetation growth carryover effect in vegetation phenology. This phenomenon, often described as a form of biological memory or biophysical feedback, demonstrating how vegetation systems retain and transmit growth relative information across temporal scales. So when we analyze this vegetation phenology, it's necessary to combine the climate factors with the physiological connections. This is my summary area. The Yang Mountain is situated at the atom between the semi-humid and semi-arid regions of North China, as the forest converges zone of Mongolia, northeastern China, and North China. Meanwhile, we extract pixels with stable vegetation type using the vegetation type data from 2000 to 2022. The stable pixels are mainly divided into 5 types of natural vegetation: broadleaf forest (DBF), evergreen native forest (ENF), deciduous native forest (DNF), shrubland (SL), and grassland (GL. The research methods are mainly divided into 3 stages. Firstly, based on modest EVI data, a street filter is used to smooth EVI time series, and dynamic threshold was adopted to extract phenological indicators. The threshold is set 20% to extract SOS and EOS. And the Pearson chain analysis and monkey test were adopted to analyze the spatial temporal dynamics trend variation. Secondly, the correlation of the relationship among physiological parameters is analyzed by correlation analysis and structural equation model. Finally, the climate response is analyzed through sensitivity correlation analysis and partial correlation analysis. First, about the research results show that on average, spatial distribution of multi-year phenology exhibits a clear northwest-northeastern divergence in terms of spatial trends. 33 areas show significant the start of season advancement. 39% show significant growth season length extension, but found no significant changes in most areas of the peak and the end of the season. From the perspective of interannual changes, there was a significant interannual change in mountain with the start of season and the peak of season has shown significantly advanced with 0.4 days per year and 0.19 days per year. And the end of season and the growth season lengths were significantly delayed and prolonged with 0.78 days per year and 0.977 days per year. And for the different vegetation types, more pronounced shifts in grassland and shrubland than the forest. Regarding the correlation of the vegetation phenology parameters, the results show that across the different vegetation types, the start of season and the peak of season shows was generally stronger and positively correlated, with a particularly high correlation in shrubland and grassland, and relatively weaker in DNF and DBF. And between the start and the end of season, and the correlation is significantly negative. Indicated that early growing up was often accompanied by delayed stances, particularly in shrubland. By contrast, the correlation between the peak of season and the end of season was weak and insignificant. Finally, the start of season expanded the growing seasons was better than the end of season. Expanded in DBF, their correlation is comparable. And the structural equation model results show that the start of season exerted a robust positive influence on the peak of the season, in particularly shrubland and the grassland, but weaker in DBF and ENF. And the start of season has a significant negative effect on the end of season, and the peak of season had a positive influence on the end of season, but the influence of the start of season is stronger than the peak of the growing season. I think as a correlation analysis, the growing season list was mainly driven by the start and the end of the season. In shrubland and grassland, the start of season has a stronger negative effect, and in arboreal vegetation types like DBF, NF, and DNF, the end of season plays a bigger role. Thirdly, the sensitivity of artificial technology to climate change exhibit significant variation across in the Yin Mountain. Every 1 degree Celsius in average increase in average annual temperature, the start of season and the peak of season advanced, but the end of season delayed and the growing season is extended. And every 100 millimeters increase in annual total precipitation on the start of season advanced, the peak of season delayed, the peak of season and the end of season all delayed, and the growth season is extended. By comparing the spatial areas and variation, precipitation mainly affected the peak of season and the growing seasons. Temperature mainly influenced the peak of season and the end of season. And also by comparing the physiological responses of different types of adaptation to climate, different vegetation types respond to climate factors is similar, but in shrubland and grassland, the peak of season and the end of season are more affected by precipitation. In other types of vegetation, temperature has a greater effect on phenology. The main conclusion of my study as follows. Firstly, the start and the peak of growth season advanced significantly at 0.5 and 0.19 days per year. Respectively, the end of the growing season delayed by 0.78 days per year, and the growing seasons extended by 0.97 days per year. These shifts were more pronounced in grassland and shrubland than in forest. Secondly, earlier the start of season advanced the peak of the season and the delayed the end of season. The start of season advancement contributes more to a growing season's extension than the end of season delay, with variation across vegetation types. Finally, mean annual temperature and precipitation jointly regulated phenological shifts. Precipitation primarily drove the start of season advancement and the growth season's extension, while temperature mainly influenced the peak of season and the end of season. My research is also in initial stage. So as follows is planned to do for future. Firstly, using multi-source remote sensing data and existing flex observation data to investigate vegetation phenology change in the region. Secondly, exercising the relative contributions of different drivers to vegetation phenological changes by integrating climate factors and the vegetation growth carryover effect. Finally, combining converse flex data to research the effects of phenology on existing productivity and water use efficiency. Thanks for your attention.
Okay. Thank you all for speakers. And this is end of our full lunch session, and we will meet here 2:30 after the afternoon session. And thank you for all of you guys being here. And after then, you guys need to help to move the chair and move the tables for preparing for lunch, and tables and chair. Please, all students and all of you guys should be help for moving chairs and tables.